So welcome to question 3 from our Shadow 2018 paper 2. It says, if P and Q are irrational and they are different, then adding them together must be irrational. We're looking to give a counterexample. So counterexamples are nice. They just mean a case with numbers where it doesn't work. So one way that you can kind of do these is, it sort of feels like cheating a little bit, but it's just sort of clever sort of reasoning, really. Irrational would be things like this, right? So how can we sort of set it up that we start with something like this, and let's say we get to a nice number, okay? You know, something like this. So maybe one way we could do it is we could say something like 5 minus pi, because it's got pi in it, it's going to be irrational, right? So you could have something like 5 minus pi, and then you could think about your goal here. So where's this coming from? This is coming from, in my head, I've got the number 5, right? So what am I going to add to this to make it happen? Well, it's going to be just pi, isn't it? Yeah? So you can sort of take one piece, take a nice piece, and have a think about how you're going to do this together. So that would work, okay? Because this is irrational because of the pi part of it. This is, you know, irrational because it is pi. And then we get to a rational number. So the idea is a rational number is something that you can express as a fraction in the form a over b in simplest form. So in my case, it's 5 over 1. All right. Now we've got another one about modulus functions. So we've got this one here. Sketch them both. They're points of intersection with y equals 0. So that's the x-axis, isn't it? Okay, so let's do the more difficult one first, which I would say is this one here. So when you have a modulus graph, the basic case of modulus of x looks like this, okay? So when you do other things to it, like say you wanted to do modulus of x minus 2, for example, well, one way you can think of it is it's a bit like graph transformation. So you can just move it to the right by 2, okay? And then when you add numbers, you just sort of lift up the graph like you normally would, okay? So we're going to basically do that, okay? So starting again, it's going to have a minimum of 3, and at 3, you'll get 3 minus 3, which will be 0 plus 2. So 3, 2 is going to be a minimum point, okay? So it looks like that. Did they want anything else? The vertex, I said the label the vertex, so that's what we just said. That was 3, 2. It did actually say sketch both on a single diagram. Okay. And their points of intersection. Well, there are no points of intersection with y equals 0 because of this plus 2. This sort of lifts it all up. So it would normally touch at 3, but it lifts it up. One thing I could do, though, if I were interested, is I could find this one out. So there's a couple of ways I could work this one out. I could put 0 in here because x is 0. So 0 minus 3. And then these mean that I should take the positive, which would be 3. And then plus 2 would be 5. So I don't think I actually need to, but just for the sake of clarity, I'm gonna label that's a 5. Okay. Okay, and then we're doing the other one, aren't we? We're doing x plus 5. So again, kind of sort of in the world of transformations, there's the idea that this is actually going to shift the regular graph 5 to the left. So it's going to be sort of over here, and the gradient's going to be the same. So it's going to have the same sort of steepness, yeah, as it did over here and as it did over here, which would be 1 and minus 1. It's also going to go through the same point, isn't it? Because 0, if you put a 0 in there to find the y-intercept, you get 5 also. So it's going to go like this. And if I just tidy this up a little bit, these should actually be parallel to each other. Okay? So let's label that as well. Let's label that as 5, not 5, minus 5, 0. Okay, and then 5 again. So that's what they would look like. Anything else? Hence, solve the inequality. So this is the purple one. This is the green one. So it's saying, when is the purple one, when does it have a lower value than the green one? Okay, well, if we extend this out over here, you can see that on the left-hand side, the purple line's always going to be higher, isn't it? So we're interested, it seems like we're interested just on the right-hand side. Now, in this sort of, let's split it up into some regions. In this region over here, because they've got the same gradient and the green line's already above, that situation's never going to change. So all the way over here, all the way over here, 3 or more, this case is true. But it's also true, isn't it, in this other region here, okay? Because at this point, the green line's still going down, whereas the purple one's going down. So this is surprisingly, when you sketch this isn't too bad at all. They're equal at 5, so I think we're just saying x is greater than or equal to 0 for this one, okay? More generally, if you wanted to know how we could solve this for harder scenarios, one way we could do it is we could notice that sort of where they're intersecting, okay? The green line, for example, is going up, so that means it's the positive case of this modulus, okay? And at this point, the purple's going down, so it's the negative case of this modulus, okay, plus 2 and you know, I might even just solve them equal. So you could sort of work with something like that to begin with, and that will give you your key values more generally. Yeah, but in this case, actually, the sketch sort of just did that one for us. So there we go. That's our question number 3.